In this class, we're going to go over all the counting methods as used in probability. These include the addition and multiplication rules, the permutations, and the selections equations. Enjoy. All right, let's make a start. So the agenda for today is going to be to cover some more probability stuff. This time we're looking at the counting methods side of things. So this is where we're essentially trying to figure out ahead of time, or these techniques can allow us to figure out how many of a certain thing that we have, how many ways could things be arranged, how many different orders can we arrange our objects, so that sort of thing. This has applications in solving probability, namely when you're looking for like sample space stuff, like how many things of our sample space apply versus don't apply. So that's where the applications come into it. It's going to start off pretty simply. We start looking at these things called the addition and multiplication principle. So these are principles around essentially how many choices you have for a particular thing. What we have a look at here is if there are m choices for one option and n choices for another option, if those are mutually exclusive, so you can't choose both, then the total number of choices you have are m plus n. All right, this will make a lot more sense when we start considering like an example being when you're ordering a main meal at a restaurant. Yes, you could order a pizza or a pasta, but when you look at the sum of all your possible choices, it doesn't really matter that they're categorized as pizza or pasta. You still just have a total of 5 possible choices as far as that's concerned. Because you can only choose one from that entire set rather than one from each individual set of pizza or pasta. So total number of choices, in this case, 5. Multiplication principle is what you use when choices are made in sequence. So even if we went back to this original example, and we assume that you might have had to have ordered a pizza and a pasta, you would have 3 choices for pizzas multiplied by the 2 choices for pastas. So you'd end up with 6 possible outcomes rather than the 5 from before. But the other example I gave was, let's say you could choose to either walk or drive when you're going towards the gym. And then once you're there, you can choose to do either cardio or weights. These are things done in sequence. You start by choosing your commute to the gym, and then you choose by deciding what exercise you want to do. Now, this is a very small sample size of possibilities, so you could literally just count out all those possibilities. Walk cardio, walk weights, drive weights. Or you could just do your m times n. So there's 2 possible choices for commute, and then there's 2 possible choices for exercise. That's multiplication principle. As far as its applications for probability, it can help you find n, and it can help you find x. So depending on what you're actually trying to solve for, it'll help for both of those. So in this case, we have an example of Jess is choosing 6 subjects. Already 3 have been chosen. For the remaining 3, we've got the following possibilities. 1 of 3 maths, 1 of 2 arts, and either 1 of the 5 languages or 1 of the 3 sciences. So there's a bit of a stack there where you're going to choose one of these, and only one of any of these. So 1 from here, and then 1 of this set here. So if we look at the total number of possible selections, you've got, let's see, there's 2 choices for the 5th subject, since you've got, your 2 arts. You've got 3 choices for your 4th subject, since there's 3 mathematics. And then when you choose your final subject, you've got 5 here and 3 here, right? So when we look at our total possibility of everything, you've got 3 choices being made in sequence, but this stack of choices sort of condensed down into each other because you can only choose one of these things. These are mutually exclusive, these are not. And so because this is done in sequence, you take the stack from each of those dot points and you multiply across. Is it clear enough what's going on there? Because that'll give you the total number of possible subject selections.
Wait, could you repeat that again, please?
Yeah, yep. So what we're looking at is trying to figure out the number of possible ways in which I can arrange my subject selections. So I'm going to choose one of 3 maths, one of 2 arts, and then to fill out that last one, I'm going to choose either one of the 5 languages or one of the 3 sciences. Now, these are choices that are made in sequence, so the multiplication principle will apply. That's why we have 3 times 2 here, 3 of these, 2 of these. But when we get here, we're only allowed to choose one of this set. So instead of going multiply by 5 and multiply by 3 again, we can only actually choose one of all of these. So instead of doing the 5 by 3, we're actually adding them using the addition principle because they're mutually exclusive. That's what like this example up here was, the fact that you can't have both, then multiplying after the addition. So 5 plus 3 gives you the 8. Is that any clearer?
Yep.
Okay. So that gives you total number of possible subject selections. We've used counting methods to figure out our n value. As far as probability of selecting a science, well, we have our n, which is totally fine. That's our divisor. To find the probability of selecting a science, our x is just going to be the number of possible sciences. And so, what did I say here? So 48 possible combinations. We're not going to list them all. Essentially, you're at a situation where only the 6th subject can be a science, because 4th is going here, 5th is going here, 6th belongs to both of these. And so realistically, instead of going through the full sample space and figuring out how many of those combinations have sciences in them, it'd be actually better off to simplify what you're looking at and say, well, this is the only place a science can go. And so with that in mind, we have 8 total possibilities, 3 of which are sciences. So the probability of selecting a science is going to be 3 out of 8. The rest of it doesn't really matter when it comes to calculating that. So you'll find this comes up a fair bit, where you won't necessarily have to do it globally. You can just look quite locally when it comes to solving probabilities, depending on the scenario you have. And that's what makes this a bit of a nastier area of study. People will either get it immediately and just coast through it, or they'll take a bit of time to really sort of find out all the shortcuts. But the good news is once you do have that, the rest of it becomes pretty stock standard once you start seeing these patterns. Is it fair enough how we've simplified that? Let me know if not. So in summary, that's addition principle and multiplication principle. If you have mutually exclusive choices, you use addition principle. If you have choices to be made in sequence, you use multiplication principle. And as we've seen, they might be used in tandem with each other depending on exactly how the scenario is arranged. That sets us up for the next couple of documents, which covers arrangements, permutations, and selections. So first up is arrangements. We're trying to figure out basically the number of ways in which a set of objects could be arranged. So the example I'm giving here, suppose you have a set of 3 objects. One way you could do that is to simply just count the number of ways you could arrange it. And you just sort of go through your sample space. You could draw a little table and just toggle things until you've figured out everything from it. That works well if it's small sample sizes. But if we get to a situation where I'm saying, how many ways can you arrange 10 objects? You probably don't want to create a 10-way table to set that up. So, easiest way to handle arrangements, and also easiest way to handle a lot of the counting method stuff we will look at, is to consider things in terms of the number of slots they can go into or the positions they could go into. So we have 10 objects and we're putting them in 10 positions, essentially. That's what it means to arrange 10 objects. You have 10 things initially, you've got 10 places you want to put them in. So you create your array that is 10 wide. Now, this is just for demonstration. You wouldn't draw the whole 10 array before filling it out. but it will end up being 10 wide. All you do is go down the list and figure out how many options do I have for each position. Well, initially, I haven't put anything anywhere. So I've got 10 possibilities to put in that first spot. Cool. Well, when we get to the next spot, we had to have chosen at least something for that first spot. So we had 10 to begin with, 10 possibilities. But now when we go to the second spot, we've actually only got 9 things left to put there. So we're going to have 9 choices for that one. You can see the pattern from here. Every time you go to the next spot, you decrement the number of possible choices, and what you'll find is the pattern will basically be a decrement by 1 every single time. And so if you wanted to figure out how many possible arrangements you could arrange these 10 objects in, well, you've got a number that, what's that, 3.62 million? Looks like it. Yeah, 3.63 million. So not great. What's up, Sanjay?
Oh yeah. So you're saying like how as we go down the list, we have to subtract like one from each number.
Mm-hmm.
So does that mean like in arrangements it's like without replacement?
Correct. Yeah, without replacement. So it's like I have 10 things, I'm putting one on the shelf here, one on the shelf there, and I'm not replacing it. Yeah, correct.
Why can't it be with replacement though?
It can be. It's just not this question. There's others where it can be, and you would still use the exact same idea, but actually I have it somewhere. It might be in the next one. There's definitely a situation where you can, no, maybe not in these notes, but definitely in one of the questions somewhere. It just depends on the question. If it says with replacement, then yeah, absolutely. Go ham and just say, look, 10's all the way through. So 10 to the power of 10 would be a number of combinations there. But in a lot of cases, you assume, unless otherwise said, without replacement. Cool.
Okay.
But yeah, no, good point. But yeah, for this one, without replacement, so the number of choices will decrement every time. This actually has a name for it. This is called a factorial. This is specifically 10 factorial because that's the number that we started with, where any number n factorial is just whatever number you start multiplied by 1 minus it, 1 minus it, 1 minus it, over and over again. So 5 factorial, for example, would be 5 by 4 by 3 by 2 by 1. 10 factorial is that. So when we look at arrangements, so far we've seen what happens if the number of positions I have is the same as the number of objects I have. Sometimes that's not the case. Sometimes you have 10 books, but only room on your shelf for 3 new books. Exact same process though, but instead of having 10 total positions, we now have 3. We still had 10 selections possible for the first, 9 then 8. 10 by 9 by 8 is going to be your number of combinations. So that works well, again, if you have a small number of things. Like even this was a bit unwieldy to have the entire 10 sets there. There's a generic formula for this, which is just you want to have n factorial divided by n minus r factorial, where r is the number of choices you're allowed to make. In this example here, it would have been 3 possible choices because you have 3 slots on your shelf, and n being the total number of options you have. So if we use this equation from the example before, we had 10 books, so n is 10. We have 3 slots, r is 3. Sub it in, simplify, simplify, and you'll see everything cancels out as required. So basically, the way to handle these kinds of questions, if you're new to this, would be expand out the factorials up to a certain point. You don't have to go nuts with it. And then see the similarities, see the pattern. And you'll see that when you expand out your 10 factorial and 7 factorial, everything from 7 down is a common factor. 7's cancel, 6 cancels, 5 cancels, all the way down, essentially. So your entire denominator will disappear, and you're just going to be left with that 10 by 9 by 8, like we saw earlier. Okay, I have another example here. So we have 3 options, vanilla, chocolate, or strawberry, and we're asked to select 2 different flavors. So one way of doing this is using the slot metaphor. So you have 3 options, vanilla, chocolate, strawberry, 2 slots. Reminder, we're supposed to select 2 different flavors. That's why we're not allowed to repeat. That's why it's not 3 by 3, for example. So we have 3 positions, possible 3 options for our first scoop. We have the 2 options for our second scoop because we've already chosen one of them. So your total number of arrangements is going to be 6. That, or just go straight for the permutations equation, whatever seems nicest to you. And then here's a list of what all those combinations would look like. Now, what's worth mentioning here is we have duplicate combinations. So you'll notice that you have, like let's say here, chocolate vanilla and vanilla chocolate, right? Some people will look at that and think, I don't care what order my scoops are in. It's the same ice cream at that point. Other people might disagree. I don't know. Point being, when you do this method of permutations, you get those duplicate combinations, which may or may not be useful. In this case, probably not as useful to have duplicate combinations. I would say so anyway. In other cases where it's like numbers, it definitely matters because the number 1, 2 is 12, whereas the number 2, 1 is 21. Big difference in the way you arrange the numbers. So depending on the circumstance you have, you might have a different approach that you use. That'll be the next thing we look at, which is called selections. But before that, we'll have a look at a few applications. So again, these are counting methods. They're helpful for solving for x or for n. Ideally, both, usually. Now, one of the interesting ones that I came across was what almost looks to be the reverse situation, where you have more positions than you have objects. So in this case, I have 10 seats on a plane and 3 passengers. Now, what's interesting about this is, at least for me, my initial thought was I have 3 passengers and 10 seats, so I have 3 things but 10 positions. I'm going to run out of things pretty quickly. It's actually better to assume the opposite. So whatever the bigger thing is, you assume that's the thing that you have to allocate. And whatever the smaller thing is, are the positions that thing can be allocated into. So even though it feels a bit weird to be giving seats to passengers rather than passengers to seats, it just works out better. So if you think about 3 passengers, passenger 1 has 10 possible spots they could go. Then because passenger 1 has chosen a spot, there's now 9 for the second and then 8 for the third. And so you're going to get back to that 10 by 9 by 8 again. So that's a interesting take on the question, I found. Sometimes you might have to reverse what feels natural to solve it. Now, this question in particular was to ask, what's the probability that 2 rear seats remain empty? And we'll get to answering that in a moment. What we've done here is figure out n, capital N, the total number of possible combinations. So without any restrictions, that's the total number of possible combinations. For the 2 rear seats to remain empty, it doesn't actually matter that they're called rear seats in this case. Really, it just matters that 2 seats specifically remain empty. Like we chop those off from the list of possibilities. So when we're calculating our numerator, our x, the number of combinations that are applicable to this probability, instead of having 10 possibilities at the beginning, we now have 8 possibilities in the beginning. So 8 by 7 by 6. And then, well, just like any other probability, you do number of combinations that meet your target divided by total number of possible combinations, and that gives you your total probability there. That's that one there. Feel free to ask any questions. I know these can be really weird.
Sorry, could you repeat that again?
Repeat up until where? Just from the start?
Like when you say like, we have to multiply 8, 7, and 6.
Oh yeah, sure. So the question was to figure out the probability that the 2 rear seats remain empty. So if it's going to be empty, it just means we can't put a passenger there, essentially, is what that means. So when you think about doing the same procedure we talked about earlier, we don't actually have 10 choices anymore. We have 10 minus 2 choices because 2 of them cannot be used. So,
Oh, okay.
yeah, you start with your 8, then 7, then 6.
Oh, all right. Okay.
Cool. Okay, now here's the reverse. What's the probability that the 2 rear seats are filled? Now, this is where it gets a bit more interesting because what I found best to work with these, and there's obviously other ways of doing it, there's a lot of other ways of doing things. What I found best to do is to try to accommodate the restriction as early as possible in your working out. So, probability that 2 rear seats are filled, basically when you're going through and thinking about the number of choices per position, you start by trying to fill out those seats. So what you have is, what did I say here? So if you think about like the first 2 positions here, those are going to be a stand-in for those 2 rear seats. So there's 3 potential passengers that could go in the first rear seat, then 2 potential passengers for that second rear seat. We started with 3 passengers, 2 of them are going in those rear seats. Then, because there's no more rear seats left, the final passenger has the 8 remaining choices available. So when you have a restriction, it's usually easiest to start by addressing the restriction first and then backfilling afterwards. And we did do that here as well, where we immediately killed the 2 seats that we weren't allowed to have at the very beginning, and then we continued backfilling from there. So overall, address the restriction first, then backfill. Fair enough how we came to that. And then when you do the actual probability, it's just x divided by n. So n usually doesn't change a whole lot. N will always just be maximum possible combinations, and that usually doesn't take a whole lot of effort to find. It's usually the x that becomes a bit weird. So that's arrangements. This is where you use arrangements if the order of the choices is important. So the number 1, 2 is 12, the number 2, 1 is 21. The order in which you write those numbers is important, and so you would use arrangements for that. Anything to clarify before I make things even more complicated?
With the example you showed us of the 2 rear seats being filled. So yeah, could you explain that again? I didn't really get it.
Yep. Okay. So when it comes to having a restriction, which you always will have a restriction in your probability, that's the thing you're targeting to try and find the probability of that event occurring. You want to start by trying to address that as soon as possible. So if I need to guarantee the 2 rear seats are filled, the first thing I'm going to do is take my 3 passengers and put 2 of them in those seats. Now, I've got a number of ways I could arrange those passengers. So when I'm looking at these first 2 combinations, these first 2 positions that I can put them in, that's going to be a stand-in for those rear seats. Now, I've got 3 people behind me. I've got 3 choices for that first rear seat. So I'm looking at that first seat, I'm saying, you, go there. That's one of my 3 choices. Then there's the second seat. I've got 2 remaining people left. I pick one of those from behind me, you go there. Then there's 1 guy left over, no more rear seats. That guy can go wherever he wants. That's what we're doing here. We're addressing the restriction as early as possible, and then whatever's left over, we give to the rest of the sample space.
Wait, but if the 2 rear seats are filled, so that means there's only 8 seats left.
Mm-hmm.
Then doesn't that mean that the first guy has 8 options?
Yeah.
Not 3.
That's that 8 at the end. So I've done it back to front, where 3 was for the first rear seat, so 3 options for that first rear seat, 2 options for the second rear seat, and then 8 options for the final guy. So the only difference between what you said and what I said was you gave the first person free reign elsewhere, and then the remaining 2 got the rear seats. I just did that back to front.
I still don't really understand. I'm sorry.
Okay, no, that's fine. Let's see if we can get a diagram going. So 3 people, 1, 2, 3. We've got our plane. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 3 people and 10 possibilities for where they could go. Now, I need to guarantee these get filled, no matter what, and then the last guy can go wherever he wants.
Mm-hmm.
So I've got to fill these one at a time. How many possibilities do I have to fill in this seat right now?
That seat.
Yeah. I'm going to put a guy here.
Mm-hmm.
How many possibilities?
3 possibilities.
Yep. So 1 guy down. Now I've got to fill in this seat. How many have I got? How many choices?
2.
Yep.
Okay.
There you go. And now 1 guy left. He can go wherever he wants. How many choices has he got?
Like 8.
Yeah. 3, 2, 8. Multiply, multiply, multiply. Bit clearer?
So I thought like the numbers like stood for like the different combinations of seats.
Oh, sure. Yeah. That was the weird bit, yeah, which was
Yeah,
I
yeah.
kind of addressed that at the beginning, which was sometimes you got to think the reverse. You want to try and arrange it in a way where the thing that you have more of is where you want to put. Hang on, other way around. Yeah, the thing that you have more of is what you want to assign to people or to the smaller group. Because otherwise, if you try to do the reverse, where you have 10 positions and then 3 things, you would have your 3 by 2 by 1 and then very quickly run out. It becomes hard to do it that way. And so arranging it in a way where you, yeah, arranging it in this way is the only real, well, one of the more effective ways, I'll say that much. There's surely ways to do it differently, but this is what I've found is a quite repeatable way of doing it.
I'm kind of scared that I might like forget how to do this.
Oh, you will, absolutely. This takes like a long time to get, which is why what I've done is I've literally done work solutions to all the stuff in these chapters because everyone fails at this. Like, yeah, I'll even pull one up so you can see. I kind of do it framework wise, so it's like here's the kinds of things I'm thinking about, and it's very repeatable. So I'll pull up one of the textbook solutions specifically for part B is arrangements, I think. Yeah. So you'll see some basic factorial stuff. That's sort of whatever. You'll see how you handle some of the more simpler examples. So like in this one here, it's how many ways can 3 pictures be hung up if there's 10 available? Well, 10 slots, 3 can be filled. So you'll see some justifications on each of the questions, and you can just sort of use this to get an idea of, well, if you're going down the right track or not.
Okay.
So that's there for you for all of these because this is a tough topic.
All right. Okay.
Cool.
All right. Cool.
Yeah, awesome. All right, so that's that one. That's arrangements. So the key issue, maybe, not really an issue, is that arrangements would give duplicate combinations. Not really an issue if the order in which you do things matters. Again, that example of 12 is a different number to 21. If, however, you don't want if you don't want duplicates in there, this is when you use something called selections, which is only a mild change when it comes to the equation. You're now going to divide by an additional r factorial, and effectively you can think of that as just excluding all those duplicates. That's the easiest way to think about that. So there was an example I gave here. How many teams can I make from a group of 4 people? So a team of Dan and Kim would be the same thing as a team of Kim and Dan. If they're on the same team, that's the same team. So we want to exclude that possibility. That's how we're going to use something like this. So if we use that previous example and we want to know how many teams we could make out of a total of 4 people, then it makes sense that each team has got to now have 2 people. So we've got 4 total people. You're going to split those 2 ways. The first team has 4 people to choose from and 2 selections to make. There's 4 total people, 2 choices for that particular team. And so to exclude all of the possible outcomes that were duplicates, you use the selections equation instead of the permutations equation to figure out what the number should go in that first position, where the position in this case just means team 1. Then from there, the second team only has 2 people to choose from because 2 have already been taken. 2 selections to make. If you go through that, there's obviously only going to be one possible way to do that, especially because the duplicates are gone. So you can think of this as being done in sequence. First, team 1 is chosen, then team 2 is chosen. That's why this array is basically just multiplication principle. You're making choices in sequence. That's why you multiply along the array. So you do it in parts, and then because you did it in sequence, 6 by 1 is 6 for your number of possible combinations. As far as the actual combinations that would lead to, if you assume these people, then these are all the unique ways you could arrange them. Any questions, let me know. Okay, so how do we actually apply this to probability? How do I get my head on straight? There's kind of 3 typical types of questions that come up. In all cases, you're using counting methods to calculate your capital N and your capital X. That's really all it's being used to do. Now, I say that's all, that is the entire question, but that's the fundamental purpose of our counting methods. So, 3 typical outcomes of questions, rather. One possibility is that the choices in your sample space can be repeated. So that's what you were mentioning earlier, which was, do I get replacement? Under those circumstances, just go straight from multiplication principle. That would be like if we went back here and it was, what was it, this one? That would be instead of decrementing the number of, where is it? Yeah, instead of decrementing the number of choices, that would be 10 by 10 by 10 by 10. If you can repeat choices, then just go straight from multiplication principle. If, where is it? If the choices can't be repeated and the order matters, then you would use the permutations equation. So this is where you're decrementing every single time, right? Permutations assumes you're decrementing, assumes there's no replacement. And it also assumes the order is important. So the word AB is different to the word BA. And then if the number of choices cannot be repeated and the order doesn't matter, so if you have a team of Kath and Kim is the same as Kim and Kath, that order doesn't matter, it's the same thing, then you're using combinations, which we just did here, or selections. Those mean the same thing, combinations / selections. That's the framework that you use to decide which combination method to use, arrangements, permutations, or selections. We're going to have a look at a few examples. So here's an example of where choices can be repeated. We want to find the number of different 4-digit numbers that can be formed from all the digits that we have access to. How many 4-digit numbers can you make from 10 digits, essentially? Now, it's worth noting there is an implied restriction in here, which is a 4-digit number still has to be a valid number as far as math is concerned. So when you're thinking about the number of positions you have 4 different positions you can put these digits in to make 4 digits, but not all choices are exactly the same. For example, there is no number in, well, at least in our mathematical notation, that starts with a 0 and is then followed up with a number. So when you think about arranging your numbers, it's not like a pin code in this example, it is an actual number. And so when you think about the possibilities for your first digit, you've only got 9 choices. You've got the numbers 1 through 9. Then everything trailing that, sure, 10, 10, 10, because now you're allowed to have that 0 again. So choices could be repeated. You can choose the same number multiple times. that's when you just go straight for multiplication principle. Fair enough? If not, let me know. Here's an example where the choices can't be repeated and the order in which you write things matters. So in the case of numbers, the number 1, 2 is different to the number 2, 1. So find the number of different 4-digit numbers without repeated numbers. So another way of saying it would be without replacement. That can be formed from the same number of digits. So again, going down the number of possible outcomes you have, first digit still only has 9 selections. We're not allowed to start with a 0 still. So that gives us 9 choices for the first one. Then when it comes to the second digit, normally we have access to the entire array of possible digits again, but we did just choose one of the numbers 1 through 9. So instead of having the full 10 digits, one of these numbers 1 through 9 is now gone. So that gives us, again, 9 selections for that second digit. And then the rest of it, well, there's nothing crazy else going on now. The rest of the digits can be whatever they'd like to be, which is why we now decrement from 9 down to 8 down to 7. And so you could do the multiplication principle directly there, which is 9 by 9 by 8 by 7, or, yeah, that's what I said here, 9 by 9 by 8 by 7. Or another way of thinking about it, if you don't like thinking about positions and that sort of thing, would be I have 9 choices for my first thing, and then the rest of it is a permutation. So I handled the restriction, which was no 0 to lead, and then I did the rest of it by backfilling. Fair enough? If not, let me know. Okay, last example, I think anyway. Choices cannot be repeated, and the order doesn't matter. So this is usually when there's teams of people that you're dealing with. Team of 3 boys, 3 girls is to be chosen from a group of 8 boys and 5 girls. How many different teams are possible? So again, you want to be in a situation where you're doing things in sequence, right? You're choosing one team, then another team, which means you want to figure out the number of combinations for any given section, and then multiply across because you're doing these things in sequence. So first things first, from the 8 total boys we have, we're choosing 3. So we're creating this team of 3 boys and 3 girls. We have 8 choices for those 3 boys. We're using selections because, again, the order in which you write 3 boys' names on a team doesn't actually matter. I guess unless one has an ego. And then for the 5 girls, well, 5 total girls, we're choosing, again, 3. So we're using selections again, 10 possible groups of girls that you could now combine. So you have the number of choices for each individual gender. All you do is total that up because you've done it in sequence through multiplication. So you total it up through multiplication. And yeah, the only thing that was required was the number of teams, so that becomes your final answer. That's the number of possible teams you could make. So that's that. I think this is just detailing more or less the same thing I mentioned earlier, except this is taking a step back now, which is how do we handle the questions in total rather than just what combination thing do I use. So what I mentioned earlier at the beginning, which was the method you use, that's step 1. You want to identify what method you're using to solve the total number of possible combinations in your scenario. So again, that'll either be multiplication principle, permutations, or selections. That's giving you NT. From there, you need to know your n of x, right? You want to know how many selections or combinations meet your particular probability. This does require intuition. I can't really say much about that. You know, we had the digit example, which meant leading digit couldn't be 0. There will be all sorts of different scenarios there. We had the plane example where you had to fill 2 back seats. You just got to use your intuition and figure out, okay, address that concern first and then backfill with how you would if there was no restriction. And then part 3 is fairly obvious. If you have n, both nx and nt, you just do your division. That is all that. So what we've done is essentially, I think, 3 or 4 chapters, maybe. How many's in here? 10A's addition. This might be 4 chapters worth of work in this one. So if it's feeling a bit overwhelming, yeah, kind of. We did do 4 chapters back to back on this. So this one might be a good one for you to go back and like watch the pre-recorded videos on them as well. And when you're doing your questions, it would also be a good idea to like refer to these work solutions that I have as well, so you can see. I'm hoping it appears fairly repeatable. I tried to write it in a way where I was using the exact same language every single time for the same thing. Not because I want to bore you and to save time, but because I want you to see that it's the same thing every single time. So I'm hoping that is the case. Yeah, unless there's anything to clarify. Ready to get into some examples?
Sure, let's go.
Let's do it. Okay, so am I right to say that it started getting tougher around the arrangements? Like, do you want to practice any of the addition, multiplication principle stuff? Just like raise your hand or jump in if you want to.
Yeah, sure.
Yeah, okay. So we'll start nice and simple, and then if it's getting too easy, I'll jump ahead. So I'll do a screen grab just in case it's easier to look at screen grabs. Otherwise, have a read of question 1 and let me know how you guys go with that. These all have the same approach, by the way.
Which question are we doing?
Question 1. So they're all the same thing. If you can do 1A, you can do 1 everything. Oh, yeah, I just saw that question. We add them, yes. Addition principle is used here. So these are not mutually exclusive. You're choosing a book, and so just because you have different types of book doesn't actually matter when you're just looking at the set of books to choose from. And so, yes, that would just be straight addition principle. So maybe one of the things I should have done was screen grab this as well. These are when you use what. Yeah, so this one would just be, 8 plus 3. This would be 3 plus 2 plus 7, so on and so forth. Nothing too crazy. Question 2 may be different, maybe not. So the first thing you got to ask is, am I doing things in sequence or are they mutually exclusive? I guess I'm not really using the word mutually exclusive super correctly there, because this does technically, like these are mutually exclusive things. When I say mutually exclusive, I mean in the sense like here, which is you can only choose one of these two things. Not necessarily that this is a different thing from this. I mean more so in the context of choices that you can make. You can only make one of this entire set. What do you think? Is this being made in sequence, or is this a situation where you're just picking one of anything? Yeah, that's correct. We're going to multiply because we're doing a sequence. We're choosing one of each. So we're choosing an entree, a main, and a dessert, rather than just one meal from the entire menu. So in all these cases, you're just going straight multiplication. 3 by 4 by 5, 10 by 10 by 5, 5 by 7 by 10, 8 by 8 by 8. So this one was done in sequence. This one was done. I'm not going to use mutually exclusive. Just say globally. We're doing it globally. Okay, let's see. Is there anything else interesting to have a look at from here? I'm just going to have a peek around through the answers to see if there's anything special to look at. Yeah, okay. Question 6 gets a little bit weirder. Let's have a look. So, have a read of that one. See how you feel. Any initial thoughts as to what might be going on?
Would you use addition principle?
You will be using addition principle in this one, yeah.
Yeah.
It's a bit more nuanced than just addition principle though, but
Hmm.
it will be helpful. So what part of this is addition principle, I guess?
Well, because so there's like three airline options from
Mm-hmm.
like Melbourne to Brisbane,
Mm-hmm.
and there's three bus line options from Melbourne to Brisbane, that same destination.
Yep.
So I guess those two are mutually exclusive.
Mm.
So that's where addition principle comes.
Yep, that's good. There's another part in there as well, which is also another potential route that could be taken, which was the double flight. So flight from Melbourne to Sydney, then Sydney to Brisbane. So the whole
Mm.
thing is you've got three mutually exclusive choices, which is direct flight, direct bus, or two-part flight. That's your addition principle. You figure out number of combinations of each individual uh, path and then add those together. But finding the individual combinations of each path, well, one of them is going to require a multiplication principle. That will be that one there. So why would that second option, the flight then bus, so why would that be a multiplication principle?
Wouldn't that be addition?
Um, well, it was choices made in sequence in this case. So the addition is around the overall path choices you have that get you from Melbourne to Brisbane. So you had one option which was fly direct, you had one option which was bus direct, and then you had one option which was fly then bus. And so the keyword then in there, fly then bus, implies that that path itself is itself a self-contained multiplication principle because it's done in sequence. So
Okay.
like you could do, what was it? There's 4 airlines and 5 buses. So you could take airline 3, bus 1. You could take airline 4, bus 2, right?
Mm.
That's why it's a multiplication principle for that particular journey. So what it ends up being is, yeah, you do the multiplication. So it's the 4 by 5, so 20 for that second option rather. 20 for the second option, 3 for the first, and 3 for the second. So 20 plus 3 plus 3, 26 in total. And I'll show you what that looks like in a bit of a neater. That's not the. Oh, we're doing 10A, not 10B. That's right. 1 second. Question 6. This might be how you arrange it yourself. You would have 3 different headings for the 3 mutually exclusive things. Figure out the number of combinations at each given stage, and then add them together at the end. Any further things to clarify from this one?
No.
Okay. Let me see. I know this one's definitely unique, 11, but let's see if there's anything else. Actually, I might not have time, so let's definitely go straight to the final question there. So, CAS style, question 11. I'll cut off the rest of them so it's super easy to know. And I'll grab a screenshot of this if you'd rather. I will say I don't think I've ever seen anyone get this right the first time. So if you do, I'll be shocked and very surprised and happy. But otherwise, happy to explain it. And even if you don't like solve it, maybe even have a discussion as to what you might start doing. Could help to imagine that M is just a number, right? So instead of worrying about the fact that there's letters in there, you could just say, stuff it, don't like working with letters. Let's just pretend M is 10. What happens then? And then potentially that could be a way to figure out a bit easier, because you can then reintroduce the m back in once you've done it numerically. Probably a good time for me to jump in, if just in case we don't run out of time there. Okay. Did anyone have anything going for them as they were solving it? Okay. So as far as how you handle this, this is one of these things where you're doing choices in sequence, right? It's again a three-course meal. We've seen this one before, which is you're choosing an entree, you're choosing a main, and you're choosing a dessert. So because it's done in sequence, you would start out with a multiplication principle. There's m choices for your entree, half m for main, m plus 1 for dessert. Done in sequence, so you multiply all together. So your total number, capital N, number of choices, is going to be the multiplication of all those things. Now, we need to figure out what the possible values of m would be such that the total number of choices is more than 1,000. So here's our equation for total number of choices. Effectively, all you're doing is saying, where is that greater than 1,000? And what m values would achieve that. So cas solve directly. If you chuck that into cas, the cas will say m is greater than 12.27. Now, 12.27, not a great number. Can anyone tell me why 12.27 is a bad number for m?
Because it's not exactly even.
Yeah, not even. Even taking a step back, it doesn't make sense to have 0.27 of a choice for a meal. So definitely want a whole number. Now, the reason why we want even is because of this half m here. If you chose m to be odd, you would end up with a decimal, a 0.5 in there. And so for that reason, not only does m have to be a whole number, but it also has to be odd. Even. Yeah. And so that's why we don't round to 13. We go 1 up once again to 14. And so a nice easy way for you to say that would be m greater than or equal to 14 with the restriction that m is an element of the set of even numbers. Now I've just said the word even there. If you wanted to be super pedantic about it, then the way to say the set of all even numbers would be, okay, now how does this? It would be something like m greater than or equal to 14, given m is an element of, do I have to say 2 and trying to think of a way to have a variable that I can multiply by 2 and then assign. Yeah, that's a tricky one to try and rearrange in a particular nice way, which uses super good set notation. I think probably just don't worry about it. If they get to that point where it's super pedantic, then I don't even think the book considered the notation for this, so not a big deal, but it will be something like this. If you guys recall, when we were looking at set notation, there was like you'd have a 2n in there, so any n that comes in here gets doubled to become an even. Potentially you could say m is an element of 2n, where n is an element of the natural numbers excluding No, actually, I think that's just fine. If you make n a natural number, m belongs to that, and then m greater than or equal to 14. That probably does it. Don't do that. That's a pain in the ass. But that does, I think, make it more bulletproof. But for all intents and purposes, just say even. All right, that's about it. If you have any questions, feel free to stay behind for a little bit. Otherwise, enjoy.